The broadcast is now starting. All attendees are in listen-only mode.
Hello and good afternoon, everyone. My name is Anna Zylik and I am with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house and all electric homes trainings to all of you. So thanks for joining us today. These trainings are at no cost thanks to the sponsors of Energize Connecticut and are part of a partnership with Connecticut Passive House. Today's training will be recorded and we will post it online afterwards. A quick reminder that as part of this training and workforce development initiative, we are offering a 75% cost reimbursement for individuals pursuing either FIAS or PHI professional accreditation. So this includes the cost of the training and the exam. And once you become certified, we'll work with you to process the 75% cost reimbursement. So if you have any questions on that, please do not hesitate to contact us. Next slide, please. In addition to this no-cost educational training series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives. Next slide. For builders and developers who choose to go all electric with their residential buildings or pursue passive house certification in multifamily projects with 5 or more units. So the passive house incentive design for Energize Connecticut is shown here and includes pre-construction incentives for feasibility studies and energy modeling, and post-construction incentives for full passive house certification. Next slide, please. The all-electric incentive is for both single-family and multifamily buildings. It offers 2 levels of eligibility with specific design and performance requirements associated for each, and has incentives amounts ranging from $1,500 per unit for multifamily up to $10,000 for single-family homes. Our goal is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you are interested in learning more, please visit our website or contact us directly at the address on the slides. And as for questions during today's session, please feel free to use the chat function throughout, and I will relay them to today's presenter, who is Joe Nebbia from Newport Partners. So yeah, with that, I will turn it over to today's presenter, Joe Nebbia. Take it away.
Okay, thank you so much for that introduction. I'm happy to be here today to talk about whole house mechanical ventilation options. Today's presentation is focused on code requirements and best practices. But I think for people who are interested in building passive house level performance, this will be an especially interesting topic, an important topic. It's an important topic in any modern construction, but especially for high performance buildings. As was mentioned before, please do type your questions in, and I'm happy to stop and go talk about whatever you're interested on this topic as we go. My plan today is to talk about why we have whole house mechanical ventilation, what the ICC codes require, as well as some other standards, what options are for providing whole house mechanical ventilation, and then talk a little bit about best practices and where we might choose one system over another, and then also common design and installation mistakes that we see, in the field, and then also what to think about with renovations. So the first topic I'd like to talk about is why we have mechanical ventilation. And I think this is an important thing to cover because there are often a lot of debates. I teach a lot of classes on energy code and on good building practices. And there's often questions about, why we're building houses so tight and so tight that we need ventilation. and why can't we just make it looser so that the home will breathe? The first thing I usually say is that the home doesn't need to breathe. It's the people inside it that need to breathe. That's an important distinction, I think, because it makes us think about why exactly we're ventilating. But let's take this argument for a minute. Why don't we just build houses loose? And then that way we wouldn't have to mechanically ventilate. Let's just get some natural ventilation blowing through. So the question first we would ask would be, how loose should it be? How much is enough air that we can get fresh air as humans to breathe? And in order to achieve that, by the way, the general accepted value is about 0.35 natural air changes per hour. So that's the volume in a space would change out about a third every hour in order for us to have enough fresh air, outside air, to breathe and have enough dilution for contaminants and all those sorts of things. That's not a pressurized test like you hear, like 5 ACH 50 or 7 ACH 50, which is a pressurized test. This is just how much air could naturally go in. And how do we change that design if we're just putting holes in and leaving natural ventilation? How do we change that design to be different on windy days? So, if wind is blowing and it's coming across the building envelope, how do we need to adjust our ventilation amount for that? What about if it's not blowing? What if we don't live in a particularly windy area? Do we need to have more holes, bigger holes? So it's complicated to try to design effectively and thoughtfully a house to have ventilation that's natural and that's effective in all situations without mechanical ventilation. There's also the argument, well, why don't we just use our operable windows? For years there was this concept in the code, and it's still some places in the code, that we can just trade off operable windows for mechanical ventilation. So there's still some mentions of that when we talk about local exhaust, in a bathroom. There's this concept that you can trade off an operable window for an exhaust fan. And the problem with that, of course, is that we don't use our windows. We know that most research suggests that people don't open their windows at all. But even if let's say I really wanted to operate my house that way, and I have a bunch of windows and they're operable and I can open them up, what do I do when it's like today? It's cold outside. Last night got down to 21 where I am. I'm sure it's probably colder where you are. It got down to 8 degrees 2 nights ago. How do I get my ventilation if I'm relying on operable windows in those situations? Or if it's an August summer where I am, it's 100 degrees a lot of days or super humid. I don't want to bring that humid, hot air into my house because I've got an open window. How long do I need to do it? Do I have to have a schedule that I'm following and getting everybody in the house to follow? How many of my windows do I open? Have I measured that? It's pretty complicated to try to get effective ventilation that way. So why we like mechanical ventilation, you probably guessed from some of the issues that I brought up here, is that it can be controlled. So we know the actual amount of air we're trying to breathe in and predicted. So I can know that I'm running it on always on basis, or maybe I'm running it every quarter hour. I know how much air I'm getting. It can be designed even more effectively than that. Maybe I do it dynamically where I'm changing my flow rates based on seasons and temperature drive, indoor to outdoor pressure drive. Maybe I can size it specifically to the space that I need and not know that, if I open 5 different windows, I think I'm close. And then we can actually test it and measure it in the field to make sure we're getting enough mechanical ventilation. So those are some of the benefits. I'd also like to talk about somewhat of a misconception about how much fresh air we need. And that misconception, to some extent, has come by how the code has developed throughout the years. I talked before about that 0.35 natural air changes per hour. That's been a reference number for quite some time in ventilation standards. But we people often say to me, well, you know, the code says I need it at 5 ACH 50. So ACH 50, air changes per hour, is a measure when I pressurize or depressurize the house at 50 pascals pressure. And so I've got a big fan and I'm measuring at that pressure level how much leakage is in that building through the building envelope. So if I have a home that's 5 ACH 50 at 50 pascals, that means the whole volume of that home will change over stale air to outside air at 50 pascals pressure. It will change over 5 times in an hour if I were to do that. So that tells me about how leaky my home is, right? And the issue is that when we introduced air tightness testing in the code, it was in 2012. It was really in 2009, but it was an option. So it was introduced in the ICC codes in 2012 as a mandatory requirement. And a lot of states didn't adopt it, but that's when it entered the code. And the target for most of the country was 3 ACH 50, but in the South it was 5. So you had to hit either a 3 or a 5 air change per hour at 50 pascals. That was an air tightness measurement or less. And when they accepted that change, there was a companion change that also went in the that was in the energy code. In the residential code, the IRC, a companion change went in that says, when you're lower than 5 ACH 50, you have to have mechanical ventilation, whole house mechanical ventilation. And the idea of those two changes, which were presented at the same time, was that if we're going to mandate air tightness in buildings, we also have to provide ventilation. The thought was we're just providing it for all homes. Everywhere in the country was going to be either 5 or 3 ACH 50, and we're going to provide whole house mechanical ventilation for all of those. So we'll make 5 ACH 50 the trigger for mechanical ventilation. But the misperception that got out there between these two code changes when it was accepted was that above 5, we were somehow safe. That above 5 ACH 50, you didn't really need whole house mechanical ventilation. And in fact, some states went so far as to say, well, you know, we're going to change it to 6 ACH 50, and that way our builders won't need to put in whole house mechanical ventilation, because then we'll be just over the line and we'll be in the safe zone. So there was this perceived danger zone. The problem with that is if you look at how much air we need, that 0.35 natural air changes per hour, in order to get that on an average annual basis. So when I say that, it's because you get different infiltration seasonally and whether it's windy or not. So on an annual basis, if we looked at the average amount of natural air changes per hour we would get for that 0.35 ACH 50, if we translate that into a blower door test, a ACH 50 number, that's about a 10 ACH 50. So in other words, my air tightness in the test needs to be 10 ACH 50 or lower to get enough fresh air annually. That's double what was required by the code. If I want good air average on a weekly basis, I really need something closer to a 14, maybe a 15 ACH 50. And that's, you know, on a typical size house kind of thing. So, you know, each house would be a little bit different. But 14, 15 ACH 50, about triple the highest allowable amount in the code since 2012, and 5 times the amount you'd have in Connecticut with a 3 ACH 50 house. So what does that tell us? I think it tells us that it's not about the code making us build tighter homes that creates this danger zone. In fact, the danger zone happened when we started adding things like OSB to our houses. So we're fully sheathing them, adding house wrap, trying to control some of the draftiness our customers were experiencing in a more open less airtight house, getting better windows, better details around the windows, just things we've been doing for the past 40 or 50 years in the building industry. So as we've built homes in a more modern way, in a way that I think the market demands, people aren't going to be comfortable if they've got constantly cold air leaking and breathing all over them. We've gotten down way below the danger zone. So if we get below 14 ACH 50 and that's in the danger zone, it really doesn't matter whether the code makes us do 5 ACH 50 or 3 or 7 or 1 or 0.67 if it's a passive house or whatever the current target is. The fact is that if we're building a house today, it has to have whole house mechanical ventilation, because builders can't even fail this poorly. They're not building 14 ACH 50s and failing their blower door tests on code compliance. They might fail at 4.5 or 3.5 or 5.1 or something like that. They're not getting 14 ACH 50 on a blower door test. And that's really how much you need to go without the mechanical ventilation. So I'll get off my soapbox a little bit on this at this point and move on to some other topics. But I hope the message that you've gotten is that we can't just choose to build houses leakier and solve the issue of fresh air. We're not going to get it without mechanical ventilation. So what do the codes require for mechanical ventilation? There's a few different places, a few different codes that cover this. For 1 and 2 family homes, we're going to find some requirements in the IECC, the energy code, where there are mandatory provisions related to providing ventilation and then the fan efficacy of that ventilation. There's also requirements in the International Residential Code. I mentioned this before, where it said less than 5 ACH 50, you have to provide whole house mechanical ventilation. And that wording has changed a little bit throughout the years. In 2012, it said less than 5, but there was this loophole where you could build it exactly 5 and get out of it. So 2015 changed to 5, less than or equal to 5 ACH 50. And then there's more updates in 2021 that I'll talk about related to that language. And then the IRC also has specific ventilation requirements in Chapter 15, which deal with local exhaust as well as whole house systems and the ventilation rates we need for outdoor air in dwelling units. There's also, if you're dealing with multifamily, the mechanical ventilation requirements are actually in the IMC, the mechanical code, and there's a specific equation that's similar to that of the IRC for dwelling units in the multifamily buildings. So if I'm trying to find out what my ventilation rate needs to be according to code, I'm most likely going to be looking in the International Residential Code, and your jurisdiction may have a different reference, but that code tells me that I can know how much ventilation I need in a home, either based on a table or an equation. So this table here is for continuous airflow. So if I've got a whole house mechanical ventilation system that I've just designed to be always on, this is telling me how much airflow I need in that ventilation to get enough outdoor air to meet the code. So if I have let's say a 2,400 square foot home, I look at that second row in the table and I see I need somewhere between, I'm somewhere between 1,501 and 3,000 square feet. So that's the row I'm in. And then I know I've got, let's say, 3 bedrooms in that 2,400 square foot home. I now know, I look at that column and I see that I need 60 CFM for my whole house mechanical ventilation. And that's an easy way to say, okay, I'm going to look at this table, pick my CFM, and get a fan that's got at least that. And I have to be designing it to be always on. if I decide that I'm going to do intermittent ventilation, which is common, so let's say I've got it on a timer to run every a quarter of every hour, so 15 minutes on the hour. If I do it that way, there's an equation in the code that says I would take that required airflow and I would multiply it then by 4, essentially, if I'm not running it all the time. So I would need 240 CFM fan if I'm only running it a quarter time, because I need to introduce more fresh air. The user in the code also has a option of using a equation to define their ventilation rate. So the equation is 0.01 times the area of the floor plus 7.5 times the number of bedrooms plus 1. So if I had that three bedroom house, I would add 1 to that number. So now it's 4 times 7.5 plus 0.01 times the area of the floor. And that's going to tell me my ventilation rate using this equation. So you can use either the table or the equation to define that ventilation rate. And that intermittent versus continuous airflow rate is going to work the same way, regardless of your choice there. But the code gives you a really nice option. And there are a few other ventilation standards that have similar structures to this for finding out how much your minimum ventilation rate needs to be.
Hey, Joe, quick
Yes.
question from the audience. Does this align with ASHRAE 62.2?
Yeah, that's a great question. I'm going to talk about 62.2 in a little bit, but I can just get into it while we've got this on the screen. It aligns in that it's the same structure. So you'll see ASHRAE has a table like this, and it has a ventilation rate equation. But the ASHRAE ventilation rate is slightly higher. So you're going to introduce more fresh air using ASHRAE. Stated simply, you're gonna use more fresh air if you're using ASHRAE compared to the IRC. They're similar, but I believe it's a 0.03. I have to look at the equation. I think it's got somewhere in here times the floor area. So it's a higher ventilation rate essentially that you're going to need, and the table reflects that as well. You'd need higher airflow if you're doing that. The ASHRAE committee has put their targets for minimum ventilation at slightly more airflow than the IRC, but the structure is the same. Now, there's more complication to that in that ASHRAE has tried to come up with ways of capturing some of the intricacies of how ventilation works and things like infiltration credits and thinking about dynamically controlled systems. Like if I'm using an air quality sensor, they're starting to talk about how they might adjust their ventilation rates. But if you just want to use the simple table and equation, you can still do that without any of the adjustments, and you would end up with higher airflow rates. Thanks for the question.
Okay, thanks.
Absolutely. And so what about for low-rise multifamily buildings? Again, there's a very similar equation here. In fact, this is exactly the same. It has instead of just saying ventilation rate, it says QOA, but it's still the outdoor airflow rate is what they call it in the mechanical code for multifamily buildings. In this section in the code, there is a big table that talks about space by space outdoor air rates. Those aren't designed for dwelling units. There's a section a little bit further down in the code, 403.3.3.1, that defines the equation for dwelling units specifically in group R234 type buildings. So you want to look at that for multifamily buildings. And again, if you look at the equation, it works exactly the same way as the single family home equation does. There's also common area ventilation rate as well. That's a little different, and that would be in the in that table, which defines space by space, what you would need to do. Also, in the I codes, there are requirements for local exhaust. So this is or can be different from your whole house mechanical ventilation system. The requirements are separate, but any of these systems can be part of a whole house mechanical ventilation solution as well. So in kitchens, we have to have local exhaust. All kitchens have to have exhaust 100 CFM intermittent or 25 CFM continuous. And bathrooms and toilets or toilet rooms have to have 50 CFM intermittent or 20 CFM continuous. So that's a exhaust fan that's going to be at these specific locations. Notice you don't do a runtime in these, so it doesn't say 25 CFM if you're running it every quarter hour, because there's some acknowledgement that people aren't going to run their bath or kitchen fan all the time. 100 CFM intermittent. You could design it to be continuous, and then you would get a lower, you could put in a smaller fan if you did that. But the 100 CFM doesn't define a specific runtime in that case for kitchens, or 50 for bathrooms. But those are required. As I said, those fans can be part of the whole house mechanical ventilation system. Depending on the size of your home, maybe it's the whole thing. Let's say I need 50 CFM intermittent in my bathroom, but I upgrade it to a 100 CFM continuous fan. Let's just say I put one of those. That's a pretty common size bath fan. I can get 100 CFM bath fan pretty easily, very quiet. I could make that my whole house mechanical ventilation system. It's oversized for that specific bathroom, but it might be the right fit for the whole house at that point. So that's an option in the code. One thing that I'd say, since we're talking about an audience interested in passive house, I know a lot of the passive house projects I've seen have used kind of what I'll call general kitchen exhaust. So maybe it's an exhaust fan on the wall or the ceiling in the kitchen to provide kitchen exhaust, and that's allowed by the code. I see that as a common ventilation strategy. What I would say is that the research I've seen suggests that they're not particularly effective compared to a kitchen exhaust that's integrated with the range, like a range hood. There's been some research done testing particulate matter levels in passive house or passive house type construction, where this approach has been used to have a kitchen exhaust that's not directly tied in with the range. And the research suggests that there was no useful dilution of particulate matter during cooking events using that general exhaust method, that we needed something a little bit more direct at the range. So it's not a code requirement, but getting into kind of best practice, a range hood is going to do a better job at getting rid of cooking pollutants, which is why we have kitchen exhaust, than a general kitchen ventilation system will do.
Hey, Joe, one other question.
Yes.
When is ASHRAE 62 used or required versus the IMC?
Yeah, so for 62, and they now kind of separate out the later versions of 62, separate out 62.1 and 2 by multifamily or single family. But let's say we're talking about a single family home. Typically where we see these come into play, ASHRAE ventilation rates, are in above code programs. So it's not required by the IRC or IMC. A jurisdiction could adopt it. So I don't know if, say, the county or city you're particularly in has required ASHRAE 62.2. It's not widely adopted by jurisdictions around the country as a code minimum requirement, even though that's what it's designed to be. Where we see it mostly is in above code programs like Energy Star. So Energy Star Homes requires ASHRAE 62.2 ventilation rates in all certified homes. And that means it's also a requirement in EPA's Indoor Air Plus program. It's also a requirement in Zero Energy Ready Home program from DOE, and it's also a requirement, all of these because of prerequisites of the other programs in the FIAS Plus program as well. And there's other above code programs out there. I'm sure I'm skipping over, but many of those require it. And it's a significant portion of that comes from the Energy Star program, which has, 100, 200,000 homes a year kind of volume. All of those homes have to have 62.2 ventilation rates. It's very seldom that it's coming in through a code process for 62.2. Hopefully that answers your question. Again, I don't know if in your specific county it's required or town or municipality, but that's where I see it most often is through the Energy Star program as an entry point. So for fan efficacy, I mentioned this earlier, the IECC, the energy code, lists specific efficacy or CFM per watt for the whole house mechanical ventilation system. Now, this only applies to that whole house system. So if I have another bath fan in the home that is not being used as part of the whole house system, I don't have to meet these efficacy requirements. But for the whole house system and anything included in it, these are mandatory requirements in the code, or they're required regardless of what compliance path I'm using. I can't skip over them in a performance path or anything like that. So my fan has to at least be this efficient, using a certain, achieving a certain level of airflow per watt of energy. And I'll note one important change here when it's by fan type, and these are minimum flow or minimum efficacies. In 2015, this top column that I'm showing here actually didn't exist, HNERV. There wasn't a specific CFM per watt required, which meant that they really fit in the inline fan category. That was the only place you could really put them. For a heat recovery ventilator or energy recovery ventilator. And the problem with that was, we'll talk a little bit more about this technology later, but heat and energy recovery ventilators are actually doing both supply and exhaust. So if I have a 100 CFM ERV, for example, that fan is moving 100 CFM supply, and it's moving 100 CFM exhaust, ideally, if it's installed correctly. So a total of 200 CFM of air is being moved using that fan. But the CFM per watt calculation is done just with the 100 CFM rating number. So in other words, HNERVs look about half as efficient as they actually are when using a CFM per watt measurement. It's really not the right measurement. And so before, in 2015, this number was 2.8 CFM per watt. And the problem was only about 5% of ERVs on the market could meet that 2.8 CFM per watt. So if you had a really detailed code official who was paying attention to the mandatory requirements, somebody might be putting a very efficient ventilation system in with energy recovery that was really performing at twice the efficacy level as what's kind of rated there. It still wouldn't comply with code. And so in 2018, there was a code change that introduced a specific CFM per watt for HNERVs that captured a lot more of the market. So most HNERVs can meet that 1.2 CFM per watt number, except the really egregious ones. And now we don't have this conflict where the energy code is pushing out HNERVs based on this efficacy number. But it is important that you check this table if you're designing or speccing a system with a a home with a whole house mechanical ventilation system and make sure that at least the fans involved in that system meet the minimum efficacy, because again, that's mandatory. You can't miss it or trade it off in a performance path or anything like that. So what's changed for the 2021 codes? I've been kind of showing a lot of slides with information from the 2018 codes. I know Connecticut has recently adopted the 2021 codes, and there are some changes related to ventilation that will be important to keep in mind. There were some changes in the air leakage testing, that blower door test. One change is that using the performance path, section 405 in the energy code, or the energy rating index path, section 406, you can actually trade off up to 5 ACH 50. So you can, if you have really hard time air sealing your house, I don't think that's going to be right for this audience if you're interested in passive house, but say a builder couldn't meet that 3 ACH 50, they have some flexibility in the performance path to go up to 5. There's also a 0.28 CFM per square foot of enclosure area test that's allowed. That's for multifamily dwellings, attached dwellings, or smaller dwellings. You can get to 0.28 CFM per square foot of enclosure area. That's a different test. It's based on surface area as opposed to volume of air change, and it's more appropriate for multifamily dwellings. Any dwelling can actually use 0.3 CFM or lower, but that 0.28 CFM per enclosure area is allowed as well. This slide actually shows it a little bit incorrectly as I'm looking at it. I'm sorry about that. So 0.28 is for those attached dwellings, or any dwelling under 1,500 square feet. 0.3 CFM is for any dwelling at all. So they can use that different measurement. Doesn't have a lot of effect for somebody who's hitting passive house levels of air tightness, though. But that is a change. Also, for climate zone 7 and 8, heat or energy recovery ventilation is now mandatory in the IECC in 2021. So not in Connecticut where you are, but if you design something somewhere else, climate zone 7 and 8, so really cold places, Duluth, Alaska, Summit County, Colorado, not where you are, but very cold places have to have heat and energy recovery ventilation now with a minimum recovery ratio. There's also a new verification requirement where there's testing for all mechanical ventilations with a few exceptions. And that's field testing, where they're testing the flow rates of these systems. There are also some changes in those efficacy tables. So we looked before, and you can see here 2.8 CFM per watt. In some cases, is changing to 3.8 or 3.5. So exhaust fans and inline supply fans are having to hit a higher efficacy level than they were in the past, a better efficacy level. If it's an H and ERV, that didn't change much, but there were some changes in 2021 on those efficacy tables. The IRC also changed, and this is important in a couple of ways. One is that the ventilation rate can be reduced by 30% in the following situation. If I have a distributed supply, so not centrally through the ventilation, the air handler, but I've actually got ducted supply to each of these locations: living room, dining room, and kitchen. And my whole house mechanical ventilation system is balanced. In that case, I can actually reduce my ventilation rate by 30%. This might be something you're interested in as a passive house builder. If you are looking at, not wanting, one of the concepts is we don't want to lose a lot of that heat that we're keeping in, right? So if we can design our ventilation system better, then we don't have to do as much air change. And that's what the IRC recognizes, and that brings it more in alignment with ASHRAE, which also has a balanced ventilation credit, ASHRAE 62.2. So that's a change in 2021 to keep in mind, that there's this ventilation rate credit, if you will, for well-designed system. It's not just any balanced system, it's one that directly supplies specific rooms. So a lot of times an H&ERV gets put in and they send it through the central air handler, which is the easier way to design it, but not as effective at ventilation delivery to areas where we want it. So if you have this distributed supply and you have a balanced system, then you get this credit. So better ventilation means you don't have to do quite as much of it. And maybe we can save some heat loss that way. In the commercial portion of the IECC, this has to do with where you might see, say, a 4-story building. Anything 4 stories is up is going to be in the commercial section of the code. Energy recovery ventilation is required in most climates, including the climate you're in. In Connecticut, if you're in the commercial section, energy recovery ventilation is required in most dwelling units. There are some size exceptions and some climate exceptions that don't apply to you, but that is a new change. It matches what's in ASHRAE 90.1, which is commercial energy code standard by ASHRAE, but it's now in the IECC as well. So most dwelling units really have to have energy recovery ventilation. That could also be heat recovery. The code term in the commercial code is actually enthalpy recovery, and there's a specific ratio that goes with that. But it is a recovery type of ventilation that could either be really HRV or ERV. One other change that I haven't seen in here, and I might actually have it later, but I'm just going to mention it now so I don't miss it if it's not in here, is that the IRC now points to the requirements of the energy code for that ventilation trigger. And in fact, I think I'm just going to stop my slideshow for a moment and pull it up in the code so you can see it. Before this, this section here said something having to do with 5 ACH less than or equal to 5 ACH 50. So this section said if your home has less than or equal to 5 ACH 50, then you have to provide whole house mechanical ventilation according to 1505. And that was that ventilation trigger we talked about. But because of some of that confusion I talked about earlier, this change was introduced. And it essentially says if you comply with the energy section, so N1102, that's the air sealing section, 1102.4.1 is the air sealing section of the energy code, which is copied into that, into the IRC. So that's what it's pointing to. It says if you comply with that section or the air sealing requirements of the code, you have to do whole house mechanical ventilation. So it takes away that confusion around if we alter the code to make it a little bit looser, can we get away without it? And that's an important change in the 2021 code. Other above code programs, Energy Star has efficacy requirements. There's also a SON rating or sound rating for fans. So we know people will use them more, won't turn them off or disable them if they're quieter. So there's a SON limit. That's not applicable to an H&ERV, which isn't tested for SONs, but for other type of fans. And then lighting requirements related to that fan system. Indoor Air Plus version 2, this is actually a little bit updated now as they've had multiple public comment drafts. So we're not sure what the final is going to look like, but when they come out with version 2, it's possible we're going to see a bump in ventilation filtration, and that there are some controls required and specific language about range hoods being ducted to outside. So currently in in a home that was doing Indoor Air Plus version 2, they could have a recirculating range hood with a general kitchen exhaust, which I talked about before, but we don't think those really work in tight houses. So it looks like Indoor Air Plus is, at least in their public comment draft, is moving toward a requirement for ducted range hoods. Surprisingly, range hoods aren't required to be ducted in the code still. I can still build a code home, and the IRC says I have to duct my range hood unless I've got a recirculating range hood. And we know recirculating range hoods don't do anything. They just spit the pollutant back out into the room. So Indoor Air Plus is moving toward requiring that system to be ducted. And you all are more familiar with passive house type construction. There's an air tightness limit, as well as having requirements about how we ventilate rooms, either directly or indirectly, with a noise limit on those fans, kind of similar to what we're seeing with Energy Star, trying to limit the noise of those fans. So if you're doing one of those programs, you're going to have to do some other things. And as I talked about before, Energy Star requires 62.2 ventilation, and these other programs adopt Energy Star as a co-requisite or prerequisite certification. And so they also include that ASHRAE 62.2 ventilation, which will have a higher rate.
I don't
So
know.
what is ASHRAE? Go ahead.
Sorry, just one question before you move on. What are your thoughts on ducting an ERV supply into the return side of the AHU versus individually ducted to each bedroom? Since VS does not allow this unless the AHU fan runs continuously.
Yeah, I think that's probably a good requirement. It's a trade-off in this type of design. So the nice thing about ducting the H or ERV into the return side of the ventilation, well, there's two kind of nice things. It gets a little bit more conditioned right before it's introduced, although the H and ERV are supposed to do a little bit of that. And it's a little simpler to design, right? In that I'm just having to duct it to one place and then let the duct system distribute it throughout the house. However, those don't tend to be very efficient. So one issue, as you point out, is there's requirements that Passive House has about having to control, having kind of an always on type system for the ventilation rate with that air handler unit. Well, I don't need my air handler to run all the time, right? Especially in a passive house, I might not need it to run a lot. Maybe I've designed my system so well that I can just run it constantly at a low level, and it's always supplying a very low level of heat. But I think that's tricky to do. So it doesn't tend to be very efficient to do it that way. And we know that it's also not a very effective way at introducing fresh air into all the spots that we would want it. So if I take my fresh air, my outdoor air, and I dump it in the central air handler, I'm then dependent on how well the duct distribution works. Is it really balanced throughout the entire house? Am I getting air to all the right places, or is more of the fresh air going somewhere and not other places, and I've got just stale air in certain rooms? So from a delivery of ventilation or fresh air point of view, it's better to supply directly to the living spaces. That's more expensive to do, though, right? It requires more duct runs, it requires more registers. So it often doesn't get done that way with H and ERVs, but we know it's better to do it with distributed supply as opposed to central supply.
Okay, thank you.
Thank you. So ASHRAE 62.2, again, we talked about this, and I'm glad I got the equation right. It is essentially, it's not quite 3 times higher, because this 0.75 times the number of bedrooms by 1, 7.5 times the number of bedrooms plus 1 is still the same, but I'm multiplying my floor area by 0.03 instead of 0.01. So that first part of the equation is going to be 3 times more than in the IRC. It uses almost the same equation, it just brings more fresh air. And in its basic form, again, there's a lot more detail, a lot more adjustment and ways to do engineered design in ASHRAE, but it is designed to deliver a higher ventilation rate than the IRC. So what are my options for whole house mechanical ventilation if I want to comply with the code? And these are currently the options in either ASHRAE or the IRC. There's a few different ways that I can do it and comply. And what I'll talk about here is what's allowed by code and the pros and cons of them. And then, of course, there's best practice and what we want to think about. For the first example is an exhaust-only ventilation. For something like a passive house that's so tight, it's unclear whether this will be. It's probably not your best choice in that you're going to have trouble with the makeup air portion of it. But it is allowed by code. So I can have an exhaust-only system. And what that means, for those of you who don't know, is that I'm forcing air out through an exhaust fan. And then I'm creating negative air pressure, which pulls air in through all the tiny cracks left in my very tight home. So if I'm at 3 ACH 50, a code level type home, I'm pulling air through all the little holes that make up that 3 ACH 50 of leakage. And I'm forcing it in. We know that this strategy is better than not ventilating. So we can measure dilution of pollutants in indoor spaces with an exhaust-only ventilation system, and that we know that we have dilution of pollutants and that we're better off with this than we are having no ventilation. The other benefits of this approach is that it's easy to design and install correctly. In fact, I might just have a bath fan that I'm putting in anyway, and I can design that to run all the time or on a schedule and make that my whole house mechanical ventilation system. If I'm just using one exhaust fan, I've only got one duct to worry about installing really well. And so I can achieve my whole house ventilation rates fairly simply, inexpensively. Again, I can get a really, really nice bathroom exhaust fan that's very quiet, 100 CFM for $100. That's significantly lower cost than some of my other whole house mechanical ventilation options. I can get a really cheap exhaust fan too for way less than that, but it wouldn't be quite as good as at delivering high performance. So it's easy to do. We see it done correctly a lot in the field. If I've just got to install an exhaust fan and put a control on it, it's fairly simple. Doesn't mean it's foolproof, but it's fairly simple and it's inexpensive. The problems with exhaust only, again, we're still pulling in our fresh air through the walls. So now my wall is kind of acting like a filter. It can be potential for condensation depending on the situation. If I've got a situation where I've got radon coming into the basement, I'm then pulling that up through the house with my exhaust fan. Now, I will say that again, studies have shown we're still diluting that radon better. It's not how we deal with radon with a exhaust only fan. We deal with it with a radon fan, right, which is specifically designed for that purpose, not the whole house fan. But if I had radon and I didn't know about it, I would still be better with an exhaust only system, even though I'm pulling things in. But I would be even better with a different type of ventilation system if I've got a radon situation. Also, I could cause backdrafting if I have an open combustion appliance, possibly depending on the amount of CFM I'm moving with those exhaust systems. And we're depressurizing the home, so those are always issues that could exist. Also, we're not controlling our fresh air supply. I don't know where that's coming from other than through my wall. And I'm not directing it anywhere specific to places where I want it to go. If I had a really leaky section, as this diagram shows, let's say I'm using my bath fan as an always-on ventilation system strategy. Well, let's say I had a really leaky window or a hole I didn't know about in that bathroom. I could be pulling all of my fresh air from that space. It's not likely to happen that way, but it's possible. And so then I'm exhausting just from that one room, really, at that point. So it's not great at controlling our supply of fresh air, but it does work to dilute pollutants in the home. Where is exhaust only appropriate? It could really be done anywhere. We see it a lot in cold climates. It's the most common ventilation type because it's the cheapest. So it's often done all over the country. If you're in a humid part of the country, so to the right of that black line running down the middle of the country there, if you're in a humid part of the country, then we'd be concerned with what kind of moisture we're pulling across the wall, right? But there are a lot of exhaust-only fans that go into places like Connecticut. One other caution on exhaust only, if you also design and build in New York, right next door, they actually have a technical bulletin in their code that says if you're going to install exhaust-only systems, you have to be able to quantify to measure both the quantity and quality of the makeup air. And so while that's not a outright prohibition of exhaust only, I don't know how you would ever be able to characterize the quality of that makeup air with an exhaust only system. So it essentially eliminates exhaust only in New York, according to how the New York Department of State interprets it. I know you're in Connecticut, but I'm sure a lot of you are designing across the border as well, so keep that in mind. Supply only is the next type of option I'd like to talk about, and that's where we're doing the opposite of that exhaust only system. We're introducing our fresh air. Often it's going to be through an inline fan in a duct that then gets pumped into the central air handler unit and then supplied throughout the house. This will have the same drawbacks, of course, as doing that through doing that system with a balanced energy recovery system. But that's something we commonly see with supply only, is that it's dumped into the return. The benefit of that is we're then conditioning the air before it's introduced. So it's not going to be humid. It's not going to be extremely cold in the winter or anything like that. And what this does is it's going to pressurize the house, which means all of the stale air in the home is going to be pushed out through all the tiny cracks in that fairly tight home. This is the second most common strategy we see across the country. It's also fairly inexpensive compared to some of the other options. And it does help us to know where our supply air is coming from. So I know I'm pumping it into the return of the HVAC unit and then distributing it throughout the house. I'm no longer using my wall as a filter, which is a positive. I'm still pushing air across that thermal boundary, though, because I've pressurized the house. And I can filter it on intake. Filtering on a supply fan is really important, especially, East Coast, we had a whole bunch of wildfire smoke this year, right? I would have liked to have a way to filter that. It's not something we commonly experience on this side of the country or haven't in the past, but we want to be able to filter what we're taking in and making sure our outdoor air is really fresh air. So those are some of the reasons we might do supply. Also, we can think about conditioning any humid air. I mentioned that before. That can be a benefit depending on where you are in the country compared to exhaust only. Some of the negatives, we are bringing in directly hot or cold air that might be humid, but usually it's being conditioned then. We do still push air across the envelope. We may not be, as I mentioned before, unless I've got duct runs to all the living spaces, I'm not sure exactly how that fresh air is going to be distributed. Depending on how cold it is, the house can feel drafty when that supply fan is running. Um, and I'm not controlling the exhaust in any way. So I'm bringing in a lot of fresh air, not doing so much on exhaust. And it does cost more than that exhaust only system. I see this most commonly in the Southeast. It is all over the country. Again, it is the second most common ventilation system, but it's very popular in the Southeast, where they found with a typical exhaust system or even a balance system, they're having some humidity problems. And so we're seeing some supply only ventilation with these. Another sort of form of this that I've seen in the past is a ventilating dehumidifier, which is a supply fan that also ventilates. But that's another kind of twist on this as opposed to an inline fan. So a lot in the Southeast is where we've seen the most market uptake. So what about balanced ventilation? Balanced ventilation is another option for our whole house system. And I'm going to call what I describe here as semi-balanced, because in this case, we're using a system of fans. So maybe it's several bath fans and the kitchen range hood, or maybe it's one really strong bath fan combined with a separate supply fan. And so we're now controlling both the supply and exhaust of our ventilation. This is allowed by code, and the benefit is we know where our fresh air is coming from. We know where that we're also exhausting and diluting those pollutants in that way. But this has to be controlled. So they would ideally, you'd have some sort of communication that would require both the supply and exhaust to be on at the same time. If we can achieve balanced ventilation where we have the same airflow for our supply and exhaust, then we don't have pressurization or depressurization. We're no longer moving air across the wall, the building envelope, and we don't have those issues of getting moisture in the walls because of how we're pulling or pushing air or those sorts of things. The negatives are that it tends to be pretty hard to design these. We have to have controls so that they work together. If they don't work simultaneously, then we could have something moving, 100 CFM exhaust, then 100 CFM air, and we're not actually balanced. We're going to be pressurizing and depressurizing. It's almost like the worst of both of those worlds as far as pressurizing and depressurizing across the building envelope. It's a little bit better maybe in that we know we're getting fresh air and then we know we're exhausting. But if it's not controlled to operate simultaneously, then we will again have a negative or positive pressure issue. Also, if I don't install it correctly, like let's say I have a supply fan and an exhaust fan, and there's a big loop, a U-bend in the exhaust fan, and so I'm actually not pulling the CFM that I think I am, then again, I've got an unbalanced system again. So it's hard to do right. It's got the same kind of drawbacks as some of the supply fans. Like we don't really know that we're getting it to all the living areas. And we're still having to usually introduce that outdoor air into our return of our supply fan, of our air handler unit. But it can be a good way to achieve balanced ventilation, both supply and exhaust, control of supply and exhaust, in a more inexpensive way than a packaged unit, which I'll talk about later. So it's two inexpensive fans as opposed to one more expensive fan. I kind of already talked about these, so I don't think I'll cover it again. Ideally, we're going to be installing balanced ventilation everywhere. So we know that supply and exhaust are limited. They can achieve minimum ventilation rates that we need them to, but as far as high performance ventilation, ideal ventilation, we want to be controlling both our supply and exhaust, and it would really be appropriate in any climate in the country, as long as we're dealing with humidity issues and conditioning that supply air as appropriate. Essentially, balanced ventilation should be the goal we're moving towards so that we can make our ventilation work correctly. Which brings me to our last option for ventilation, that type that would be allowed by code, which is a heat or energy recovery ventilator. If you don't know how these work, it's a packaged unit that has both supply and exhaust duct runs. In some cases, they're connected to the air handler unit. And in other cases, they're distributed supply, as I talked about before. And what these systems do is, as they're both supplying and exhausting, they're recovering some amount of energy. For a heat recovery ventilator, they're exchanging heat, usually through like a ceramic core or something like that. It's not actually crossing the air streams and mixing supply and exhaust air. They're just taking, in the winter example, they're taking heat from inside and crossing it across that core, which is then used to heat the incoming supply air and make the impact of that cold, fresh air less on the energy or the heat load of home. For an energy recovery ventilator, there's an enthalpy core, which is like a membrane usually, and that's actually saving energy by exchanging moisture. But either one of these systems can save energy compared to a balanced system, and they also save energy on the heating and cooling system compared to, say, an exhaust system. So they do save energy by the fact that they're doing that heat or enthalpy exchange in the system. They're also controlling both supply and exhaust. So we know where our supply is coming from. We know where our exhaust is coming from. We no longer have depressurization or pressurization. And unlike a system of fans achieving a balanced effect, we can do it with one unit. So it's easier to balance in that way. Here's just an example of an energy model that did some analysis, and you'll see here I've got an exhaust-only system and a heat recovery system side by side, and I'm analyzing the energy. And you might see here that down in the lower left corner, I've got $1,003 in annual energy costs in heating, where I only have $872 in heating with the heat recovery ventilation. So I'm saving on my space heating, excuse me. I actually use a little bit more cooling energy, but still in balance, I'm using less heating and cooling energy. But if you look in lighting and appliances, I'm actually using more heat recovery ventilation energy, because that heat recovery system is both supplying and exhausting using one fan compared to an exhaust fan. So if I had a 100 CFM exhaust fan and I had a 100 CFM HRV, I'm moving 200 CFM of air. So this equation looks a little better if I were to compare against a balanced system, which it has both supply and exhaust fans, and then I wouldn't see that uptick in appliance energy use. But overall, I see that it's a win. I'm using $2,296 in energy costs versus $2,374 with the exhaust-only system. So even though I'm using more fan energy with this system, I'm actually saving money overall, and it's from that heating system savings where that's coming from. And this is just one example. You know, you could do analysis on any home you were doing to see how that would impact the energy model. Once I've decided that balanced ventilation is my goal, then that heat recovery ventilation or energy recovery ventilation looks like a lot better comparison in this energy comparison. So what are some of the cons? They are more expensive. And so that's the primary barrier, right? Is that they're costing more than other things I can do to achieve my code compliance. They can be harder to design. I'm not sure they're really harder to design than, say, a balanced system with multiple fans that has to have controls, but certainly compared to an exhaust or supply only system, they're harder to design and install. There's also some amount of maintenance that needs to be done on some of these systems. Some of them have a condensation line, like a heat pump would. Some of them have or most of them have a filter that should be changed. So there's some maintenance that has to happen with them, which is different than an exhaust-only fan, right? We want them to have filters because then we're not pulling in unfiltered outside air, but that does add some complexity. But I think the cost is probably the main barrier to these systems. Where are they appropriate? This is an interesting debate because even among designers of fans, there's no consensus about whether heat recovery ventilator is always better in the cold climates and energy recovery in the southern climates, or the moist versus dry climates. I've seen energy recovery ventilators done in Seattle, where it gets pretty cold, and I've seen heat recovery ventilators done in Texas, and they were done effectively. So it can depend on what other things you're doing. What's your heating and cooling system look like? Are you doing supplemental dehumidification? And some of these sorts of things can drive the choice of H and ERVs. But as I said before, we want balanced ventilation everywhere, and an H or ERV is going to save us energy anywhere in the country if we install it. The question is going to be, can we make it cost effective? It looks like I've got about 15 minutes left, or 17 minutes left, so I'll try to go through these last sections a little bit quicker than I've been going, but hopefully this information is helpful to you. So for ducting mechanical ventilation, again, we have to think about whether we want to go direct for a supply to the rooms or through the air handler unit. And I've already talked about the pros and cons of those, so I'll just move on from that. For other requirements, there's usually a requirement, or there is in the code, that there has to be a manual override. So the homeowner has to be able to turn it off, essentially. We like to advise people to do something in the homeowner manual that says, don't turn it off, please. There's also a lot of new research going on about demand controlled ventilation using indoor air quality sensors. One example of that might be carbon dioxide sensors, where I'm using that as a proxy for how many people are in the space. And I say, okay, if I've got more people in the space, I need to boost my ventilation. Another thought is maybe we could measure indoor air pollutants like particulate matter or nitrogen dioxide, or maybe we measure relative humidity and use sensors to kind of control our ventilation rates. That's still kind of a developing field, but it's something that I know some leading edge builders doing passive house level type design use CO2 sensors for a boost on their whole house system, or particulate matter sensors for a boost on their kitchen range hood, or to have an auto on function that might override the typical schedule on that system when we need more fresh air. For multifamily buildings, there are some differences, obviously, than a single family building. One is that you could do it a few different ways. We could do unit by unit systems where we're supplying and exhausting from each unit, or there could be a central system, as is shown in the middle, where we're both we have a central supply trunk and an exhaust trunk, and those will go to the units. They serve each of the units, but the exhaust and supply is handled by one large commercial system or several large commercial systems with this central trunk, and then distributes from there. That's allowed. Both of those approaches are allowed by code. What's not allowed by code is that ventilation isn't supposed to be pulled from a corridor, which was a common supply strategy for a long time, or from an adjacent dwelling unit. So here are some examples of good and bad practices, most of them bad, but we want to think about where we're installing something. The location can make a big difference. We don't want to install, as is shown on the left here, in a place where I immediately need to do a U-bend with my duct to get where I'm going, to get that stale air to the outdoors. I'm immediately losing CFM that way, and I don't want to have to do that. So we have to think about our location as we install a fan and where the duct is going to need to be, so that we can not immediately cut our ventilation airflow down. We often see issues where the fan is not sealed to the finished surface, so then we might be pulling air just in a kind of from the attic space above or something like that, and exhausting that instead of the air from the living space where we want to exhaust it from. Or we've got flex duct that's not sealed well at the connection or something like that, and then we don't have the airflow we're desiring because we're leaking a lot of air. We see duct runs that are too long, right? We see them and shown on the left here. It's like ending kind of by that attic vent. It's not actually duct to the outside. That's not really allowed by code. Hasn't been for a long time, but we still see it a lot. A lot of U-bends and poor location in ducts. We want to make sure that we're properly sealing all duct connections. So if there's a chance to put mastic or UL listed tape on that duct in addition to the mechanical fastener, that can help to make sure we're not leaking. We want to make sure our exhaust fans, where they penetrate the building envelope, are sealed to the finished surface. And then when we're at our exhaust termination, we want to make sure there's sealing at that termination to prevent both water and air intrusion at that location. We want a pest screen on that to make sure that pests can't get in the exhaust duct. They have to be properly supported. These are pretty simple things, but you'd be surprised how often they're done incorrectly. For renovations, as I talked about before, the new home market is air sealing naturally by how we build homes, and we can achieve much better levels of air sealing in something like a passive house. So from my point of view, in a renovation, it's always a good idea to air seal if we can also deal with ventilation. So if we're doing a renovation and the scope of work doesn't include a ventilation upgrade, we may need to think about that before we air seal that existing home, and think about whether we're exacerbating a problem of lack of fresh air that at least was better, if not completely solved, when it was leakier. Again, I don't think that natural ventilation through leaks is an effective way to ventilate, but we don't want to make the problem worse during a renovation. So we need to make sure we address that ventilation at that time. Kitchen remodels, one of the most important things we can do in a kitchen remodel is to duct the range hood to the outdoors. Not only does it cut down on sound, even with the same fan zone ratings, I'll cut my sound dramatically by ducting that range hood to the outdoors compared to a recirculation system. But we know that kitchens are a major source of indoor pollutants. PM 2.5, particulate matter of 2.5 microns per inch is something that we know causes long-term cardiovascular and pulmonary health issues. It's the size of the particle that's the problem. And it can be the contents of the particle as well, like if it's a carcinogen. But the size of the particle, regardless of what it's made of, is going to lodge in our lungs and then enter the bloodstream. And it causes all these heart problems. Particulate matter is created in both all electric and homes with gas cooking. So we focus a lot on eliminating gas cooking these days, but we really need point exhaust to get rid of particulate matter in the kitchens, because we're always creating PM 2.5 regardless of the fuel source, because it happens when we're burning, when oil is being aerosolized, when water boils, if there's minerals in the water, those are aerosolized and they're causing creation of particulate matter anytime we're cooking. Nitrogen dioxide, again, it's worse if we've got gas cooking, but we need to think about it regardless. Most of the generation is from gas cooking with that. We have a lot of pollutants, though, that are generated by cooking. So we need to make sure that we're effectively ventilating, and ducting the range hood is one of the most important ways that we can do that. We do need to think about how well the range hood looks. We know that, for example, capture efficiency, how much of the pollutant range hoods capture is not particularly good across the industry. There is a test method out there right now to test capture efficiency, but it hasn't gotten to the point where it's in wide use because they're having trouble replicating the results of that test. But people are thinking about capture efficiency. We know we want to duct it to outdoors. We could think about having the range hood run anytime the stovetop or the oven or the range is on. We could use a thermostat control or just some kind of interlock control so that it's always on. One of the big problems with range hoods is that people don't turn them on. So if we can find a way to make that automatic, maybe it replies to a PM 2.5 sensor, maybe it replies to just a heat sensor telling it, hey, somebody's using the range, you should turn on. Also, making range hoods quieter is a way we can prevent the homeowner from turning it off, because if it's not loud and noisy, they'll be much more likely to use it. So for remodels, the same ventilation rates are required. So if in the scope of the remodel, I'm having to change that ventilation system, when I'm adding a bathroom or something that would need ventilation, then I would have the same flow rates as would be required in that kitchen. If I need makeup air, which is if the range hood is more than 400 CFM, in later versions of the code, it's if there's unsealed combustion equipment in conditioned space, then I would have to have makeup air as well. So I need to think about that if I'm installing, if I'm doing kitchen renovations, changing out that kitchen ventilation. For ASHRAE 62.2, you can have demand control, which doesn't mean sensor control. It means manual on or off or automatic. Again, it's at 100 CFM, or there's this 5 ACH 50 measure you can use for the kitchen. It's a little more confusing. That's also used in like Energy Star and stuff, where I'm using a volume change out instead of a specific CFM on the fan. But that is allowed according to ASHRAE 62.2. And there needs to be a readily accessible manual control present in those cases. Bathroom remodel, again, always a good idea to add ventilation while we're remodeling the bathroom. How many of us have been in a bathroom that was built a long time ago and an operable window was installed instead of an exhaust fan? It's always humid in there. So I'm going to go in and I'm going to change out the toilet and the sink and the faucet and the tile, and I'm going to redo the shower and make it look really beautiful. And then I don't do the exhaust fan, and I've got humidity and I've got mold and the drywall's cracking and there's all sorts of problems. If I'm remodeling a bathroom, I want to make sure I've got an effective control of moisture in that space, especially with a good bath fan. Again, the CFM required would be the same. Have to duct it to outdoors, 50 CFM intermittent or 20 CFM continuous. That's the same as new. And for 62.2, it's required always compared to the IRC, which allows that operable window trade-off, but the same ventilation rates are required. So we want to make sure it's not noisy. We want to make sure that the ducting is done correctly and where we're terminating it. A lot of times you put in a new bath fan in a remodel. Sometimes there wasn't a bathroom there before, and it's not even connected to a duct, or it's connected to a duct and somewhere in the attic. We need to make sure that those are done correctly in a renovation. And we also want to make sure that we're limiting the length of that duct, keeping it as straight as possible, and thinking about where it terminates on the outside as well, not right next to a window. It can't be within 3 feet of the window. those sorts of considerations we need to think about. Whole house mechanical ventilation, that's pretty tough. We only have about 5 minutes left here, but I'm going to talk about it briefly. On a whole home renovation or broad renovation, we're going to be limited in our system type choice. Often the easiest thing to do is add or upgrade the bath fan, put a control on it so it runs all the time and do exhaust only. Because it's in a renovation, we may not have access to a better design system. If we have a basement or something like that where we can put an H&E RV, maybe we can adequately duct more high performance ventilation system in a renovation. But what I would say is important is that if we're doing any kind of renovation, we're likely going to make the house tighter, because if we touch the walls at all, we're going to have to put more insulation in. Those walls are going to have to meet at least the prescriptive air sealing requirements of the code. And so we need to make sure our ventilation is adequate no matter what from a whole house standpoint. So closing thoughts, we want to be air sealing. We want to control how much energy we're losing through air leakage, but we need to ventilate to remove pollutants from the house and introduce the fresh air that we need as humans to breathe. We know that compliance is an issue with ventilation, so it's important that we're paying attention to doing it right. And when we're building tight, which we're always doing now, at least tight enough to put us in the danger zone, we want to be ventilating. I hope this has been useful to you today. As was mentioned at the beginning, there are AIA CEUs for this, so please respond to the questionnaire afterward with your information. If you want learning units, we can certainly process those. Here's my contact information briefly, and I don't know if there's any final questions. We have about 2 minutes left here.
Hi, yes, Joe, there are. This is going to go back a little bit to your earlier slides. Most all range hood wall caps are leaky. Do you have any recommendations for good quality ones, good quality units?
Well, I'd probably get myself in a little bit of trouble if I'm going to give a specific brand recommendation. But what I would say is that most of those, if I'm picking a range hood, I can do some on-site air sealing to mitigate some of those problems. If I'm understanding your question correctly. One thing I would say, though, is that if you're using like an over-the-range microwave as your range hood, there's essentially no way to do that well. And so you're always going to have a poorly performing ventilation system that doesn't pull air well, doesn't do well on capture efficiency, and is fairly leaky if you're using your microwave as your ventilation system. That's the one comment I have. I would choose a real range hood as opposed to a over-the-range microwave. Put the microwave somewhere else. But as far as a good versus bad range hood, I don't want to get myself into trouble with a specific brand. But I would say that my solution, if I was installing it, was to take whatever I had, look at the box, see where I'm likely to have leak points, and do some on-site air sealing in the unit itself at the duct connection, making sure the cutouts are right, because a lot of units can be either recirculating or ducted. And so I need to make sure that it's configured for the ducted approach. And that might mean I've got to seal up some other holes or ports that were in there for the recirc system. And that would be important. Hopefully I got it at what you were asking there. I think it's 1:30. I don't know if you want to ask a final question or not, or if you just want to end there.
Sure, yeah, let's just add one last one. Do you prefer unitized ventilation systems or central rooftop systems in a multifamily building?
That's a great question. I prefer unitized. And when I say that, I mean, I know that in each unit, I can measure the ventilation, airflow, and exhaust, and I can control it. I do understand that there's a trade-off there with cost and number of penetrations in a building. So I think we can be more effective with unitized multifamily ventilation, especially if I'm doing a balanced system. But I understand the draw of a central system because I have fewer penetrations. I might not have space in my multifamily building. So there are some design considerations about whether I can do unitized in a multifamily, but that would be my preference if I were to be able to design the unit around the ventilation system, I would do unitized.
Okay. Thanks, Joe. Yeah, it's 1:31, so we're gonna have to call it an end here. But yeah, thank you for this great presentation. And yeah, like Joe mentioned, we are having AIA CEUs for this training today. So I will send out a survey to collect everyone's info on that. And yeah, thanks everyone for joining, and thank you to the sponsors of Energize Connecticut for bringing this presentation today. Thank you.
Okay, thank you so much, everyone.
All right. Have a good rest of the day. Bye.